So I will wait for one more minute before start. Okay, so let's get started. And okay. Okay, so welcome back. And we were in the middle of discussing the imperative programming language, which appears in chapter 2 of the textbook. So can everybody hear me? Would you say yes if you can hear me? Okay, good. Thank you very much. So we are in the middle of discussing the simple imperative language, and the purpose is not really about, studying a new programming language. It's more about learning tools that enables you to analyze key features of these language. A programming language like this one that we are talking about. Also, imperative feature is one of the key concepts or key, in a sense, big design principles of modern programming languages. So we looked at, the imperative programming language is just like what you see, what you experience in your daily life, which is like a Python and Java. In most of the languages, you already tried it before. And then the syntax of the language we are talking about looks like this. It has integer expressions that we talked about when we discussed the predicate logic or the language for integer expressions. Also, it has a Boolean expressions. So in a sense, this language has two types of expressions, one for integers, the other for Booleans. And then they are distinguished syntactically by the syntax. And then the main thing in this language is a command. And then there are 5 kinds of commands. One is skip, assignment, sequential composition, if-then-else statement, and while statement. And as I said before, if you happen to work on programming languages or present your idea for, say, compiler or hardware, if it's relevant to programming languages, then often this simple programming language is the one people often use to present their ideas, because it forms the core of modern imperative language. And then I said, now this is a syntax, and you perhaps have a good understanding about what each of the constructs should mean, but we want to formalize its meaning using denotational semantics. So we want to map each of the phrases, the abstract phrases in this language, into some mathematical entities. But then I said, giving a denotational semantics in this context is a bit challenging, or it requires some more ideas. That's because of the while loops. So if you think about the while loops, so here's a while loop. Intuitively, we are expecting if you unroll the loop once, and that will give the same meaning. So in this case, it should mean the same thing as this if-then-else statements, where we unroll the loop once, so check B, the condition of the while. If it's not true, then we get out of the loop, so we skip. Otherwise, we execute the body of the loop once and then go into the while loops. And then if denotational semantics follow the principle that I told you, which is case analysis, and then essentially use recursions to use the inductions to use semantics of subphrases, then this definition of this denotational semantics of the right-hand side of this equation will have the form that you see on the screen, which is so some mathematical formula and then somewhere the semantics of subphrase, which in this case, which come from here, its meaning will appear somewhere. Also, that meaning may appear some other places as well. What that means is that the semantics of a while has to be a fixed point of some function f. But I said in the last time, not every function has a fixed point. So we have to be a bit more careful about what kind of f here can actually arise when we define the semantics. It does have a fixed point in our setting. That's because this is the kind of function that can be defined by a program. So some of you who may heard about or may took a course on computability theory or theory of computation, that's also the place where we study what kind of functions can be defined by a computer, because they are talking about computable functions. So here we are doing something similar. We are focusing on the kind of function that can be defined by a program. But there's a big difference between computability theory and the particular theory I'm going to talk about, which is called domain theory. Computability theory, you can think of it as very low level, very detailed descriptions about what kind of things can be written by a program. In domain theory, it's more approximate. It captures some aspects of definable functions by programs, but it's not really go all the way down and it doesn't try to characterize those functions completely. And John Reynolds said this, we're gonna identify this using what we call domain theory. So we identify this using so-called domain theory. And one way to understand domain theory is it's a different type of theory of computation, or maybe you can think of it as approximate theory of computability. So we are talking about computability in a bit different way. They focus on the limit of communication. So here the communication means communication between input and output. So one of the things that's going to be captured in this domain theory is that in order to produce a finite amount of information in the output, a program only needs a finite amount of information from the input. I know that these words won't make too much sense to you at this point, but it will become clear when we discuss domain theory. And yeah, so the finite amount of input output can be seen. If you imagine a program that take a stream as an input, which is a sequence of, say, numbers as an input, and produce a sequence of numbers as an output, then you can see that in order to produce a finite subsequence of the output, the program can only look at finite subsequence of the input. It can't really look at the infinite sequence that's given as an input. So the domain theory captures of this type of, the limitations of what kind of things we can write in a program. Okay. So that brings us to the next topic, which is a domain theory. I think it's number 3, perhaps 4. So conceptually, domain theory, you can think of it as approximate theory of computability that focus on some different limitations of computations or computable functions. But mathematically, you can also think of it as it's a kind of a theory that will allow us to define the semantics of a while. It will allow us to say when certain functions have always a fixed point. So that's another way, more like a practical way of understanding the domain theory. The key, and then there are very high-level heuristics that's employed by domain theory, which is also employed by many other theories like topology and so on. And then the high-level heuristic is now I'm going to explain domain theory purely based on when there's a function f have a fixed point. Okay, so we want to set things up correctly so that in order to, we will ensure function f, which is defined a certain way, will always have a fixed point. And domain theory will ensure that there's existence of a fixed point. Now, how you do it? And then here's a high-level heuristic. The high-level heuristic is that instead of thinking, when we talk about functions, we talk about its domain and its range and so on, but which are typically sets. But the high-level heuristic that's employed by the domain theory is, instead of thinking about set, we will consider set with some structure. And this structure is going to be a binary relation on the set. This is sometimes called approximation order. And this approximation order, in a sense, describe which outcome is, in a sense, it describes how the computation proceed. Okay, so I'm going to explain what it means more precisely later. But it's a set with some structure, which is binary relation. And then the other, also it has some property. And then the other thing that we are going to do is that we will only consider functions between such sets that preserve such. That preserve those structures. So these are the things that we're going to consider. So instead of arbitrary set, we'll consider set with something extra, some extra information that we're going to put. And then when we talk about functions, instead of thinking about arbitrary functions between the set, we will ensure these functions preserve structure that exists in the input, the map, just like a homomorphism that we talk about when we discuss the initial algebra. Okay, now, so how does it work? So here's, I'm gonna give you a bunch of definitions for the domain theory. And so give you definitions. Mostly it's about the first item is about structure. So the first definition is the notion of poset, actually partial order. A partial order on a set on a set S is a binary relation. Yes. So we're gonna denote this binary relation as like less than. So binary relation, it means that this less than is a subset of S cross S, such that it has certain properties. So what are the properties? The first property is it's reflexive. So which means that X is less than X for all X in S. So this notation means because this less than is the subset of, it's a set of tuples, this is really means X comma X is in the set of tuple, but the one that I wrote is the more common notations. And then the second property is transitive. Which means that X less than X, Y, and Y less than Z. That implies X less than Z for X, Y, Z. Then the third property is it's an anti-symmetry. Which means X is less than Y and Y is less than X. That implies X and Y should be the same. So if binary relation satisfy these three properties, we call it as a partial order that satisfy this reflexivity, transitivity, anti-symmetry property. And then a set with a partial order is called a poset, partially ordered set. It's called posets or partially ordered set. Yes. So poset is because it's short. I mean, that's the terminology that people are using. Okay. So what's the example of such a case? I mean, one version examples. So some simple examples are like, I mean, we have the set of natural numbers, like a 0, 1. I mean, I will first write something very, very simple, which is I consider two element set, which is something called bottom and top. And then the binary relation relate bottom to bottom, top to top, and then bottom less than top. So this is a very simple examples of a poset, which consists of two elements. Bottom is smaller than the top. That's what's going on here. And pictorially, we're gonna express this using like, I mean, draw things like this. Sometimes this is called Hassel diagram. And this means that I mean, there are two elements, bottom and top is larger than bottom. And then, I mean, things can relate to itself because of the reflexivity. That's what should happen. And so the something below is smaller than something above. Okay, so that's one example of a poset. And then another example of poset that's very familiar to you is a vertical natural number. So which is in computer science, we start with a 0. Mathematics often start with 1. So 0 is the smallest element, 1 is larger than 0, 2 is larger than 0, and I mean to 1 and so on. Of course, I mean the one above, like a 2, is greater than 0. So this is a specific partial order that you are familiar with. So that's an example 1. Another example. But here, partial order can be something extremely simple. So another very simple partial order like this, I mean, for the natural number, we can do the same, but let's take for a set of integers, but we don't order anything. So that we just said there are a bunch of elements, -3, -2, -1, 0, 1, 2, and so on. But nothing is smaller than the other. So the here integer z in x is less than y if and only if they are the same. So this is sometimes called discrete partial order. And it is a partial order because it is reflexive because of the equality, and then anti-symmetric, and also it's transitive because, I mean, in these conditions, in the transitivity, say x is the same as y is the same as z, so x and z should be the same. But that's another examples of the partial order, which means that every set can be considered as a partial order poset. Then some more interesting examples is lifted partial order. So for the z, you often write it something like this, which means same as z, 1, 0, 1, and 2, but we add some extra element called bottom that's smaller than everything else. So numbers like 1, 2, I mean, they are the, in a sense, maximal elements in this set, in this poset, but there is one element which is smaller than everything else, which is called bottom. And two more examples, I mean, the other example is this sequence of integers. So finite sequence of integers. It consists of finite sequences like empty sequence contains 1, some contains 2 and 3, maybe 4, 1, 2, and so on. And then the order we are giving is a prefix order. So we said sequence alpha is less than equal to beta if alpha is a prefix of beta. And then the one in the right. So the examples are like this sequence 1, 2, smaller than 1, 2, 3, 1, because 1, 2 is a prefix of the second sequence, but 1, 2 is not not smaller than 2, 3, 1 because it's not a prefix. Okay. The last bit that I want to talk about is a power set. So I think I use this notation. This power set, I mean, sometimes in my notes, I write it like a P of Z. So both of them are notation for the power set, which means that this one contains subsets of Z. So you can get 1, 2, minus 1, minus 4, maybe even the entire set Z, maybe all the odd numbers and so on. So, and then the order, the less than, so two subsets of A and B. A is less than B, if and only if A is a subset of B. Okay. So this is another quite common partial order. So, right. Okay, so then what's the next condition? So partial order is just something that you perhaps learned in a discrete math course. And then there is some more important bit that we're gonna talk about now is that we'll define a predomain. The predomain is a poset S, and then its order is a predomain if every chain. So I'm going to explain what this means, but every chain has the list of bound. So here, I mean, there are two things which I didn't quite explain to you. The first thing is, what does it mean, chain? Chain, so let's say every chain in S. So what's the chain? Chain is a sequence of elements inside S. So let's call it the sequence. Yeah, I think for sequence, this is better notation. Sequence Xn, where n is in natural number. It's a sequence. So you can visualize it as x0, x1, x2, and so on, where each of the elements are in S, such that it's increasing. So x0 smaller than equal to x1, x1 is smaller than equal to x2, and so on. If that condition is satisfied, this is called chain. And what's the least upper bound? This least upper bound of this chain means it's some element y in S, such that you take two properties. It should be an upper bound of this chain. So xn smaller than equal to y for n, and then so this means upper bound, and it has to be a least upper bound. That condition means for any other upper bound, for any y prime in S, if xn less than y prime for n, in other words, y prime is also an upper bound, so then x is smaller than equal to y prime. So in some sense, what does it tell us is y is an upper bound of all the x's in the sequence, but it's the tightest upper bound. Any other upper bound is larger than this upper bound. So that's what this means by the least upper bound. This is property of our list. So poset is called a predomain. If it satisfies this property, every chain, you can think of it as every increasing sequence has the least upper bounds, then we say that this poset is a predomain. And then just tell you one more definition. The one more definition is now a predomain by the way, so before talking about this definition, we say this least upper bound. You can show that that least upper bound has to be unique. So that's why we can use the article the here. So there is only one least upper bound for every right. So let me. So and then the upper bound. Where is? Okay. And then this least upper bound is often written as this notations, xn. So, and you can, if you want, you can write it n0 to infinity, or say xn, n is in natural numbers. So least upper bound is written using this square cup notation. Okay. Now for, let's say the predomain is predomain Sn less than is a domain if it has the smallest least element this element of which we denote by bottom. Okay. So a predomain is a domain which has the least element. What does this mean? The least element means the smallest element. So it has some element which if you write it as a bottom, so then it has to satisfy this property. Bottom should be less than x, less than equal to x for all x in S. Okay. So that's called a domain. And these are the key players in domain theory. I mean, so here's one exercise I want you to do. So we go through some examples, that the 4 examples that I showed you above. And then for those examples, I want you to check which one is domain and which one is predomain. Okay. So here are examples. So then exercise is for all these examples, show which one is domain and which one is predomain. So here's an exercise. So which one is a domain? So that's the first exercise. Second exercise is, now if this one happens to be that not a domain or not a pre-domain, find a way to convert it to a pre-domain or a domain. So if it's a pre-domain but not a domain, find a way to convert it to a domain. If it's not even a pre-domain, find a way to convert it to a pre-domain. Okay, so these are the two exercises. I'll give you maybe 4 minutes to solve all these questions. That's right. I mean, the chain, when Hichan asked whether in a chain element has to be distinct, they don't have to be distinct. So chain has to be infinite, but it doesn't have to be distinct. So it's a countable infinite, but it doesn't have to be distinct. Okay, so let me answer the question. The first one is a domain, which means it's also a pre-domain. And actually, there's one simple heuristic that you can, or some kind of rules that you can use to check whether it's a pre-domain or not very easily. And as Hee-chan pointed out in the chat box, if you have some domain, some set posets, and all the chains you can think about. So what are the big heuristic or some methods for checking whether S is a predomain? We're quickly checking. So some easy way to do it is that whether it has what John Reynolds called interesting chains. But what does it mean is it's a chain where the number of different elements in the chains can be infinite. Okay, so let's think about the first example. It has only bottom and top. So if you create a chain which contains like x0, x1, x2, and so on, then this chain cannot have infinitely many different elements because there are two elements only. So there will be lots of repetitions, and then because it's a chain, it's either or bottom, or at some point it will change to top and then it will remain top. So that's the only chains. Okay. So in a setting like this, then it becomes automatically a predomain because every chain in this case, so if maybe non-existence, if it doesn't have any interesting chain, which means if every chain in this case is essentially stabilized after a certain point it becomes the same element, continue to be the same element, then the same element in the chain, so it will become like x1, x2, x3, but it remains like x4 forever. So in this case, x4, because it remains x4 forever, list upper bound is going to be x4. Okay? So if chain is not interesting, then the elements which, in a sense, the chain converge, or which the chain remains the same, that's going to be the list upper bound of the chain. So chain will always have a list upper bound. So let's phrase it again. Non-interesting chains always have the list upper bound, and that list upper bound appears in the chain. So because of this A is a predomain, and then also it contains the smallest element bottom. So that's why it's a domain. Now let's use the same reasoning to check number C. C is a predomain because here, if you have a chain, then less than means two things are equal. So that every chain in Z is gonna be uninteresting. They will not contain infinitely many different elements. They will be uninteresting. So they will all have the list upper bound there. By the same reasons, the second one, the D is also a predomain. That's because, in this case, the chain will be essentially starting with, if we start with bottom, either it remain at bottom or it will go to some number and remain there forever. Okay. And then this Z, this one is not a domain because it doesn't contain list elements. But this one contains a list element, so it's going to be a domain. Now for N, it's not going to be a domain. That's because we can create an interesting chain which have infinitely many different elements. And what the chain is going to be? Chain in this case is going to be 0, 1, 2, and so on. That's an interesting chain because it has infinitely many different elements, and it's not going to have a list upper bound. It will keep increasing whatever element you pick in, and it's not going to bound this entire sequence. So this is not a predomain, but you can make it to a predomain by putting top. So if you add something called the top, which is not any of the natural numbers. So we add top to all the natural numbers. And if you add them, then if you have a sequence like 0, 1, 2, and so on, its list upper bound is going to be top. And in fact, the set N together with this extra element top. Sometimes it's called infinite, and that's going to be actually a domain because it also have a smallest element, which is a 0. Now let's move to the next and see number F, the power set. I mean, this is a domain. Let's use red. So it's a domain, and the list element is empty set. And then if we have a chain like x0, x1, and so on, and then list upper bound of this xn is going to be defined by union. So each of these x's should be a subset of z. So we can take, I mean, it's a list upper bound notation. So we can just take their union, and that will form the list upper bound of the chain. Okay, so this is a domain. The one on this z star, it's not a domain for very similar reason as these vertical natural numbers. That's because we can create a sequence, in this case, like starting from empty, contains 1, contains 1 and 2, 1, 2, 3, so on. So in this type of the sequence which keep increasing will never have a upper bound, upper bound in this G star, because G star only contain finitely many, finite sequence of finite size. So in order to make this as a domain, common way to do it is putting infinite sequence. So I put so-called infinite sequence of omega. So this means that we have this type of finite sequence, as well as we have a sequence like 1, 2, 3, 4, so on. So infinite sequence is also going to be included. So every finite as well as infinite sequence, if we include all of them, this will become a domain. List element is an empty sequence, and then the limits, the list upper bound of the chain, all the list upper bound of all the interesting chains will be given by infinite sequence. Okay, so I hope you get some idea. So C is a pre-domain. So so number C. Okay, so in the number C is a pre-domain. That's because here, if you think about any chain, so chain is an increasing element, x0, x1, x2, and so on. And because the less than relationship is true only when two things are equal, this implies x0 is equal to x1, x1 is equal to x2, x2 is equal to x3, and so on. Okay. So then, in this case, how can you find the list upper bound? List upper bound, I mean, this LUB means list upper bound. In this case, it's defined to be this x0, because every element is the same. So then list upper bound can be the same element. So that's, I mean, this is fall into this case. It doesn't have any interesting chains. So if you have a chain, essentially after a finite point, it becomes a constant. So that's why this one has the, every chain in this case has the list upper bound. That's right. So that's, we are not really using order, the typical order between natural numbers. We are using the particular order, discrete order, where two things, A is less than B if and only if they are the same. So that's why sometimes this Z is called horizontal Z. This N is called vertical N. So we can also think about vertical Z, which have the usual order. No, list upper bound of the given chain is the elements in the chain. Okay, so we have that's typical, let's think about specific chain. Okay, the one chain is number 3, 3, 3, and so on. So now if you pick number 4, 4 is not an upper bound, right? 4, this 3 is not an upper bound bounded by 4. Only 3 is upper bounded by 3. So in this case, its least upper bound is only 3. Okay. Any other questions? Okay, good. So just to come back, we defined 2 concepts. One is pre-domain and then domain. Now here comes something really, so these are the structure that we're gonna impose. So we sometimes consider the pre-domain, or sometimes you consider domain in domain theory. And often some convention that I'm gonna follow is that for pre-domain, gonna use, instead of S, use a P less than these notations. For domain, I'm gonna use a D less than 2, means that indicates I'm talking about pre-domain and I'm talking about domain. So then the next important bit is this concept of continuous functions. So if suppose that we have a pre-domain, P1, another pre-domain, P2, these are the pre-domains. Then suppose we have a function f that goes from P1 to P2. So then we want to talk about some properties of the function f. So the first property says that we say f is monotone if it preserves this less than relation. So what does this mean? This means that if for all x1 and x2 in P, if x1 is smaller than or equal to x2, according to the P1, so I write the P1 to indicate what's really going on here. So that implies f of x1 is less than or equal to P2, f of x2. Okay. So the P preserve the order. So that's what this monotonicity means. Then continuity can be defined directly. That's what the John did in the textbook, but we're gonna define in this way because it will make things a bit easier. So we said f. So let's just say. So when f is monotone, we say that f is continuous if it satisfies the following property: continuous. It preserves the limits of a chain. The least upper bound of every chain. Chain in P1. Okay, so what does this mean? This means that if it said it preserve the least upper bound, and what does this mean is if you pick for any chain xn in P1, which means visually, which means that we have x0, x1, x2, and so on, and that all is in the source of f. Then if you apply f, because f is monotone, if you apply f, we're going to have another chain. This is, so the chain in P2. Okay, so this is, if you apply the function f, it's going to be the chain. You will have a, because P2 is the domain, pre-domain, you will have a list upper bound, but this list upper bound will have the form. Chain has f applied to xn list upper bound. Okay, so that's what this means. And more mathematically, I mean, this part can also be expressed by saying, for every chain in P1, if you apply f to the list upper bounds on xn, that gives the same result as applying f to each xn and then take each list upper bound later. So limit preservation, the list upper bound preservation is what's called a continuity in this case. Okay. So for some of you who took a course on topology or maybe analysis, you heard about continuity from the math courses. There in topology, you said continuity means every open set in the target, its inverse image is open, so that's how you define it. And the same kind of a characterization can be given here as well. So there is some topology in domain theory related topology, which is called Scott topology. And this continuity coincides with the continuity from topology. But if you are not familiar with topology, it's completely okay. Just remember continuity means the preservations of the limit of every chain. Monotonicity means preservation of the order. Now, so suppose that there are the third conditions, property that I want to talk about. The third is that, okay, what's the third is if, suppose P1 and P2 are domains, which means it has a list elements. So it has a list, the first guy has a list element bottom 1, second guy has a list element bottom 2. So suppose this is the case. So then we set functions f that goes from P1 to P2 is strict. So typically we are only usually consider monotone functions. But actually we usually consider continuous function, but we said it's strict if we preserve the bottom, preserve the smallest element. So continuous function doesn't have to preserve the smallest element, but this is some extra property, and this is called the strictness of a function. Okay. So here's definition for continuity, monotonicity, continuity, and strictness. So let me give you some example for. So some simple example is, think about a function f where we set in vertical natural number, which is 0, 1, and so on. Then we also talk about this another domain, which is mapping, only have a top and bottom. Let's think about a map that maps all the elements except top to bottom, and then it maps top to the top element there. So, and this function is not continuous. So this is some function, let's say f. If then f is not continuous, it's monotone because it preserves the order, but it's not continuous. That's because now if you think about a chain, which, so say x0 is equal to 0, x1 is equal to 1, x2 is equal, well, let's make it more interesting by, you make just all the even numbers, 1, 2, 4, x3, 6, and so on. So if you do this, then it's a list upper bounds of xn is equal to top. Now, if we apply f to list upper bounds, and that's going to be applying f to tops, that's going to be tops in the target. But for every xn, if you apply f to xn, that's going to be applying f to 2n. That will be equal to bottom. So list upper bound of f of xn is going to be a list upper bound of bottom, and that's going to be equal to bottom. I mean, sequence which contain all the bottoms is bottom. So this is not, this is a violation of continuity property. It's strict because 0 gets mapped to the bottom. Okay. Now, what's the then example of continuous functions? So one example of continuous function is actually something really simple. Is that let's think about in this domain, the z bottom. So it's a horizontal measure, the integers with extra bottom. So sometimes this is called lifting. So we have -1, 1, -1, 0, 1, so on. Now let's think about any of the other domains. Let's say the target is P, okay. Free domain. So it's a free domain. And let's assume that there's a function f which is monotone. So then this function will be automatically continuous. Okay. So we only assume that f is monotone, but if that's the case, then f is automatically continuous. And the reason is the reason is essentially that the source of this function f doesn't have any interesting chains. Okay, so what's the continuity means? Continuity means that f xn is same as n of f of xn. Okay. Now, by monotonicity, so one thing we know so let's now go to the monotonicity. If this function, because the sequence here in the source doesn't contain anything, is not very interesting, which means that there exists some xm0, which is the least upper bound of this guy. So this one is same as f of xm0. Now, both this f of xm0 is of course smaller than equal to least upper bound of f of xn, okay? Because the right-hand side is upper bounding for all these f of xm, right? So this is coming from monotonicity. And this one comes from absence of interesting chain. Now, then how you get, so this means we prove the left-hand side is less than equal to the right-hand side. But the other case is actually true for every, this is always true for all monotone functions. 감사합니다. It's true for all monotone functions, including f. The reason is xn is smaller than equal to this upper bound of xn. So call it xm is less than equal to this upper bound of xn. because the right-hand side is an upper bound for every element in the sequence. So by monotonicity, f of xm is less than equal to f of n xn for m, which means that the right-hand side, this is an upper bound. So that upper bound should be greater than the least upper bound. This is a least upper bound, so the least upper bound should be smaller than equal to the right-hand side here. So this, what I told you is, the one directions, this direction is always true because if its function is monotone. And this is the other direction. This is the difficult direction, but this difficult direction is actually, that's the direction that continuity actually require. That direction is true in this example. That's because we don't have any interesting chains. Okay. So in the remaining 15 minutes, I'm gonna talk about two things. One is give you the proof of least fixed point theorem. And then I will give you, but before doing so, I will give you some informal words which may or may not help you understand, gain some intuitions about what's really going on. So a large part of the work on programming language theory is a bit like a phenomenology. So there are some phenomenon called a programming language. We want to provide a right mathematical formalizations of what's really going on. And that formalization has to be abstract enough so that it's convenient to use and then to prove some theorems. So in this case, if you're now coming back to this domain theory, the key components in the domain theory is this less than relation, right? So, and then it talk about, it has a key component of domain theory is this less than relation. Let's maybe going back all the way. So it's a less than relation, and it say there has to be some property regarding the less than relation. So then the question becomes, what this less than relation actually models in terms of computation? Okay, so that's some question we can raise. And if you go back to this example, and especially I think this particular example is better. So what this less than relation model is not about something is smaller than the other. It's more about if you wait for the computations, how the output of the computation may change. Okay, it's a bit like describing a movie or some order between scenes in a movie, where the movie is about producing the output of the computation. So what does bottom means in the application that we're going to talk about? Bottom means that so imagine that you are running some program, and then while you are running the program, it will take some time. So in the beginning, the program will not output anything. So bottom in the specific applications of domain theory in the programming language, bottom means we haven't got anything yet in this program which produce an integer as an output. If program go into the infinite loops, it will remain into the bottom forever because it's not going to produce anything. But if it outputs and some number, it will output number like 0 or 1, and then it terminate immediately. Okay, so this domain Z bottom is describing very simple kind of progressions in this integer producing computation. Bottom means no output is produced yet, and then 0 or some other things means that something is produced. And the order captures this idea that which kind of evolution is possible in this setting. Absence of information to some number is possible because absence is something that we experience when the program is still doing some computation. And when computation is finished, it will produce number like 0. Okay, so the order here expressed that initially no information is available in terms of for the output, but at some point some specific number will be produced. Now, so some students ask why we don't put an order between 0 and 1 and so on. Here we don't put an order because if the program that we are thinking about change the output from 0 to 1, okay, so then we may put an order to model such a situation. But if you think about the programs that produce like a Python program that returns integer as an output, it's not the case that it first returns 0 and then later it changes its mind and return 1 for the same input. I mean, for the same computation. That's not what's going to happen. It doesn't produce an output. At some point, it finishes the computation, it will produce an output 0, then that's fixed once and for all. So that's the kind of situation that's described here. Now, the situation for this vertical natural number is different. It's more like, suppose that your output that you have is a counter, okay? So initially, it's more like interactive program, and then it instead of producing output as a final definitive answer, the program give us some number, like initially gave us 0, and it will increase that number from 0 to 1, 1 to 2, maybe 2 to 10, and so on. Okay, so if the program keep updating its outputs by increasing it, and that's the kind of computation that can be modeled by this n top. Okay, and then program may be going on forever without terminating, and keep increasing this output value. So that's what is one of the scenario described by this sequence here. I mean, the 0 is less than 1, 1 is less than 2, and so on. And then the other example, which is actually one of the key examples in domain theory, this example is like this. So just like I told you in the beginning, this is stream processing program. And right, so this is a stream processing program. So imagine a program that takes that produce this output. So then initially the output was an empty sequence, but suppose that whenever the computation completes some part of it, it produce a number and add it to the end of the sequence. So then from the empty, it might produce the number 1. So then the sequence produced so far is going to become sequence containing 1. Maybe if you produce 4, the sequence will contain from 1 to 1, 4, and so on. So the order here is again describing if you keep waiting for the output, what kind of progressions of the output you will be able to observe. So that's very different perspective from the normal computability theory. Okay. So in a sense, the order describes the order between the scenes, and then this is sequence is a bit like a movie of how the value of the output has been changed throughout the computation. If you don't understand what I'm talking about, that's okay. I mean, it's some informal words which may help you, but may not help you. Okay, so the remaining 7 minutes, let me just show the key results. So here are the key technical results for. Okay, so here's some theorem called the least fixed point theorem. What does the theorem say? The theorem says the following. Suppose that we have a domain. Let's make bottom explicit. This is a domain. And we have a continuous function on that goes from D to D. It's a continuous function. So I'm not saying it's strict, so it's just preserve, it's a monotone and it preserve the limits or least upper bounds of every chain. So if that's the case, then there exists X in D, which satisfies the two property. First, it's a fixed point, f of x is equal to x. Second, for any other fixed point, x is smaller. So for all y, if f of y is equal to y, that implies x is smaller than equal to y. So this intuitively means x is the least fixed point. Okay, so I mean, actually, there is only one least fixed point. So actually you can say, yeah. So it satisfies these two properties, and the notation. Okay, there's no notation. So that's a key theorem, and then now we can ask why why this is true. By the way, this is the kind of theorem we need to give interpretations of the while loop, because as I said before, to give us semantics of while loops, we need to show the certain functions have a fixed point. Now, how can you prove this? Proof is actually not very difficult. So what kind of information we have for domain? The information we have is we have a bottom. Other information we have is that every chain in the domain has a limit, least upper bound. So we construct X as follows. So the first step that we do is that we build a chain. Okay, the chain is we start with the bottom. So this is chain. Why this is a chain? I mean, this order is always true because the bottom is the smallest elements. Now, if you apply, because function f is monotone, if you apply function f to both sides of this less than relations, we have f of bottom less than f of bottom. So that's exactly in this relationship is exactly the relationship required for the second. And if you keep repeating this, you get to the same thing, you get a relationship for the third, and so on. So you can prove that this chain, this is going to be an increasing chain. I mean, this is going to be a chain. So the chain, we will write it like x of n bottom. If n is equal to 0, it's bottom. Otherwise, we're applying n multiple times. Now, because this is a chain, we can compute this least upper bound. And then we said x is the same as the least upper bounds of this chain. Right, say it like this. Now we claim this is the fixed point. So the first question is x a fixed point? And the answer is yes, because if you apply f to x, because of the continuity, it's the same as applying n equal to, let's make it explicit, 0 to infinity to fn of bottom. Because f is continuous, that's the same as n is 0 to infinity to f of n bottom, same as infinite f of n plus 1 bottom. But this means that we are computing the least upper bound of a new chain, but which looks the same. So this is talking about least upper bound of new chain, which looks like this, f n plus 1 bottom n. If you compare these two chains, the two chains are the same except the first element. This first chain contains extra bottom, second chain doesn't. But for two chains, this extra bottom doesn't make any difference at all because it's a smaller, I mean, it doesn't really affect the least upper bound. So this one is same as upper bound, n is 0 to infinity fn bottom. So we just adding extra bottom doesn't make any difference. So that just shows that this is same as x, shows x is a fixed point. So give me 1 more minute, then I will complete the proof. The second part of the proof is it's a least fixed point. So now consider, so pick y in D, which is a fixed point. So then, well, one thing you know is we can actually show y is an upper bound. Of the chain Fn bottom. And why that's the case? I mean, why this relationship is true? Because of bottom. Now, if you apply F, this is because of the monotonicity, we get this, and that's the same as y, because y is a fixed point. So y is greater than F1 of bottom. If you do the same thing, then y is the same, greater than equal to F2 of bottom, and so on. So y is an upper bound. So then we said this x is the least upper bound of the chain. Upper bound the chain. So what we know is that x is smaller than equal to y. Okay, so this is precisely what's required, because we said we need to compute fixed point, and the fixed point has to be smaller than equal to any other fixed point. Okay, so that's it for today, and we're gonna continue from here next week. So I will be here about 5 more minutes. So if you have any questions, you can ask me.